Hello everyone, and welcome. In this session, we'll learn what pumps are, why they are needed, and how different types of pumps work. A pump is a mechanical device that raises, transports, or pressurizes liquid by converting mechanical energy into hydraulic energy. Pumps and compressors deliver energy to fluids, while turbines extract it. Pumps are used to move liquid from low to high pressure, increase flow rate, or lift it to higher levels. Pump head means the height or pressure a pump can raise a fluid to a key factor showing its performance. Pumps are mainly of two types: positive displacement pumps and non-positive displacement pumps. Positive displacement pumps include reciprocating types, piston, plunger, and diaphragm, and rotary types, such as gear, screw, lobe, and vane pumps. Non-positive displacement pumps include centrifugal pumps, radial and mixed flow, and jet or propeller pumps, also called axial flow pumps. Positive displacement pumps, or hydrostatic pumps, move fluid by trapping a fixed amount and forcing it into the discharge pipe. They deliver a constant volume, even if pressure changes, but produce a pulsating flow. Ideal for high-pressure, low-flow applications, they handle viscous fluids, emulsions, and precise dosing. Examples include reciprocating, gear, and vane pumps. Non-positive displacement pumps, or hydrodynamic pumps, deliver a smooth, continuous flow with constant pressure but changing discharge. Energy is added via rotating blades, converting to pressure as fluid passes through larger areas. Suited for low-pressure, high-flow applications up to 20 bars. They need manual priming and handle large volumes of low-viscosity fluids. Examples include centrifugal and propeller pumps. Centrifugal pumps lose efficiency with thick fluids and changing pressure, and require priming. In contrast, positive displacement pumps handle thick fluids well, are efficient across pressure changes, are self-priming but produce a pulsing flow. A reciprocating PD pump uses the back-and-forth stroke of a piston, plunger, or diaphragm. This action creates a pulsating flow that can cause vibrations. Using multiple pistons out of phase minimizes pulsing. Plunger pumps handle higher pressure than piston pumps, as their seal is stationary, reducing wear. Let's see how these pumps work. All types use the same two strokes. First, the suction stroke draws fluid in as the piston or diaphragm retracts. Then, the compression stroke pushes the fluid out under pressure. This simple suck and push cycle is what makes piston, plunger, and diaphragm pumps work. Now, for rotary PD pumps, instead of a back-and-forth stroke, these use spinning gears or lobes to move fluid. The rotating parts create a seal, suck fluid in, trap it, and carry it to the discharge. This provides a smoother flow than reciprocating pumps. Common types are gear, lobe, vane, and screw pumps. Let's look at some common rotary pump designs. An external gear pump has two meshing gears inside a housing. An internal gear pump uses one gear inside another. A lobe pump has rotating lobes that don't touch, and a vane pump uses sliding vanes in a rotor. Each design is perfect for different fluid handling needs. A centrifugal pump works on a simple but clever principle: centrifugal force. Think of spinning a bucket of water. The force pushes the water outward. Inside the pump, a spinning impeller does exactly this, accelerating the liquid and converting mechanical power into kinetic energy. Then, as this fast-moving liquid passes through the volute casing, it slows down, and that kinetic energy is transformed into the pressure that pushes the fluid through your pipes. A centrifugal pump's operation is an energy conversion process. Prime mover energy spins the shaft, which rotates the impeller. The impeller's vanes impart kinetic energy to the fluid, flinging it outward by centrifugal force. This high-speed fluid then enters the volute casing, where it slows down, converting its kinetic energy into pressure energy to be discharged from the system. Let's look at the three major parts of a centrifugal pump. First, the shaft. It transmits the motor's power and supports the rotating parts. Next, the impeller. Its vanes spin and directly transfer hydraulic energy into the fluid. Finally, the volute casing. This curved housing surrounds the impeller. As the liquid moves through this expanding volute, its velocity decreases, which efficiently converts that speed into pressure. Now, let's look at the three main types of impellers. An open impeller has vanes free on both sides, ideal for dirty fluids. A semi-open impeller has a shroud on one side, offering a balance of strength and clog resistance. Finally, a closed impeller has shrouds on both sides of the vanes, creating the most efficient design for clean liquids. This is a critical point. Centrifugal pumps must be primed before starting. Unlike positive displacement pumps, they cannot create suction if the impeller is spinning in air. Priming is simply the process of completely filling the pump casing and impeller with liquid, pushing all the air out. This is absolutely essential for a first startup, and it's a best practice to prime the pump before every single operation to ensure it works correctly and doesn't get damaged. Let's see how priming works. We start with a pump full of air. To prime it, we add water through a priming port, which pushes the air out. We keep filling until the entire impeller and volute are submerged, with no air left inside. Once the pump is fully packed with liquid, it can create the necessary suction to pull fluid in and push it out through the discharge. Centrifugal pumps are also classified by how the fluid moves through them. In a radial flow pump, liquid enters axially, but is flung out at a right angle to the shaft, creating high pressure. In an axial flow pump, the liquid enters and exits parallel to the shaft, resulting in very high flow rates but lower pressure. A mixed flow pump is a hybrid. Fluid exits at an angle, giving a balance of medium pressure and high flow, making it a versatile middle ground option. We can also classify centrifugal pumps by the number of impellers. A single-stage pump has just one impeller and is perfect for high flow at low pressure. A two-stage pump uses two impellers to generate a medium head. For very high-pressure applications, we use a multi-stage pump, which has 3 or more impellers in series, with each impeller boosting the pressure further. Another key design difference is how fluid enters the impeller. A single suction impeller allows liquid to enter from only one side. This is a simple and common design. A double suction impeller, however, lets fluid enter from both sides simultaneously. This balances the axial thrust on the pump shaft, reduces wear, and allows for a higher flow capacity. The volute casing also comes in different designs. A single volute has one flow channel and a single cutwater. It's simple and used for smaller low-capacity pumps. However, it creates unbalanced radial forces on the impeller. A double volute solves this by having 2 separate flow channels and cutwaters, positioned 180 degrees apart. This balances the radial loads, reducing shaft deflection and vibration, which is why it's the preferred design for most larger centrifugal pumps. Pumps are also designed based on how the impeller is supported. In an overhung design, the impeller is mounted on the end of the shaft, like a cantilever with bearings on only one side. This is a compact design. In a between-bearing pump, the impeller is mounted between 2 bearing supports. This provides much greater stability for heavier loads and is essential for larger, more powerful pumps. Finally, let's look at shaft orientation. A horizontal centrifugal pump has its shaft lying sideways. This is the most common type, prized for its easy access for servicing and maintenance. In contrast, a vertical centrifugal pump has its shaft oriented upright. This design is ideal for applications where space is limited, such as in wells or sumps, as it has a much smaller footprint. Let's cover 2 crucial terms. First is cavitation. This is the formation and violent collapse of vapor bubbles in low-pressure zones around the impeller. The implosions create intense shock waves that erode metal, destroy the impeller, cause severe vibration, and drop performance. It's a destructive phenomenon you must prevent. The second term is slip. This is the internal leakage within a pump. It's the difference between the theoretical flow it should deliver and the actual, lower flow it does deliver. Slip is why a pump's real-world output is always less than its ideal calculated output.